All right, so we're going to talk about regression, and we're going to talk about how we get a line of best fit, and then we're going to talk about how our calculation of least squares in least squares regression to get our line of best fit correlates with an ANOVA table, breaking down the sources of variation associated with a regression analysis, and then how we can use those sources of variation to come up with a generalized score that can be fit to a distribution to tell us the probability of getting a line of best fit due to chance alone. And maybe the first way to start doing this before we even get to any numbers is to think about regression generally in terms of when you're going to get a result that is due to chance alone. So the first condition I'd like you to consider is a situation where you have an x and a y and we only have 2 points in our regression. So think about how many ways you can connect those 2 points with a line of best fit. Trick question, of course. There's only one way to do it. There is a perfect line that goes between these 2 points. And due to chance alone, if there's no real relationship between x and y, how often are you going to find a perfect line that goes between 2 points? The answer is every time. Every single time. And so it doesn't matter if there's a real relationship or not, you'll always find a line of best fit between those 2 points that's perfect. Does it mean that that's real and that there's a real relationship between those 2 things? Absolutely not. Because any 2 points, regardless of what x and y are here, will form a best fit line. So you can imagine all sorts of scenarios where you just measure 2 things and you can find a line of best fit connecting them. So we don't know if the third time we measure something if we'll get a point out here or a point out here, and all of a sudden there's no line of best fit, and instead we just have a flat line that would best go through those points. So the whole point of a regression analysis is that we often don't find ourselves in a situation where we only have 2 points. We don't find ourselves in a situation where we have too many points. Sometimes that'd be a good problem. Usually we're somewhere in between, and so we end up with a situation where maybe we have something like this, where we have some points scattered on the graph. It looks almost like a shotgun pattern that would have no correlation value, no strong regression value, but we can fit a line through it. Maybe our line looks something like this. And what we want to know is, would we get this pattern due to chance? Okay, our other question might be, how strong is this pattern? These 2 questions are the fundamental questions we have to ask about every regression relationship. 1, would we get it due to chance? And 2, how strong is that pattern? These relate to 2 really important measurements or 2 really important calculations we'll make, and 2 really important values that we're going to get from our regression that are really important to keep in mind. When you're doing an ANOVA or a straight ANOVA comparing categories, when you're doing a chi-square, when you're doing a t-test, all these other tests, you have one value that you're really paying attention to at the end, and that's called the p-value. The same thing is true here. We're going to have a p-value, that's a probability value, and we're going to hope that that probability value is less than 0.05 as a general rule, though you can set your own p-value, but this is a common one. So small p-values indicate no, we wouldn't get this due to chance. There's a low probability of getting this due to chance, getting this pattern due to chance. How strong is this pattern? In this case, is going to finally relate to an r squared, or for multiple regression, capital R squared. the difference isn't so important right now, but so we can stick with lowercase r squared. It's all the same. But r squared in this case really is, especially for simple regression, it's very similar to a Pearson's R, a correlation analysis R squared. So that it's going to go from 0 to 1, and most of the time it's going to be somewhere in between there, and you can think of that as a proportion of your variation that's explained by the line. And that tells you an index of strength. So the closer you are to 1, the more perfect the regression analysis is in terms of strength. Let's talk about the strength part first, because this is where we got our line of best fit from. Or it's related to our measurements of line of best fit, excuse me. So if we take each of these points, of course, we might say that there is an overall mean here. It might look something like this, okay? And we might first say that we could look at the distance of these individual points to the line itself. So there's a distance from each of these points all the way to the line. I'm going to extend my line up here a little bit so I can get my last point there. And that one's going to be 0. So if you remember, we calculated first our sources of variation in our R squared table. And so we started with the y hats minus the y bars. Y bar would be represented here. And each point here along the line associated with a given value of x is going to be a y hat. So we have a y hat sub I here, and a y hat sub I here, y hat sub I, y hat sub I. Okay, so each point along a line is going to be a y hat sub I, and then we have a y bar here. So the first thing that we calculated in our table was we did a summation of all of the y hat sub i's minus the y bars squared. And this was variation that was associated with the regression line itself. So in that case, we took each of these y hat sub i's and we looked at the distance to the overall mean here, right? Okay. So we took all of, in this case, it would be all of the pink dotted lines that I just drew, going from a y hat sub I, subtracting off the mean. And so we're really saying, how much does that line deviate from an overall mean, from an overall average? How linear is it, and how different is it from just using the overall mean? One way to estimate something about a group of samples is just to use the mean. That's where we started. So a regression, fundamentally at its core, is testing the hypothesis. What's the difference between fitting a line to these points and just calculating the overall mean and using the overall mean as our best estimate? So we're really comparing how good is the mean compared to the line, ultimately. Okay. You'll remember that our line of best fit was associated with minimizing the error term. And you'll remember the error term was associated with these first black lines that I drew here. And so that's going to be our y sub i's, and each one of these points here is our actual y sub I, right? Y sub I there, y sub I there, y sub I, y sub I, and y sub I. And you remember our error term was going to be the summation of our y sub I minus a y sub I hat. Okay, so that was going to be the next level in our regression. So we started off with error due to regression. We'll draw this out as a table in just a second. And then we had error associated with how far is each point from the line itself. Now remember, this is what we tried to minimize. Min equals line of best fit. Right? In other words, this is where we got our least squares regression. Right? That's our least squares. So we minimized that. Okay. So that's another way to think of variation in this data set. So our first question was, how far is that line from the mean on average using our values? That was our pink here. Then in black here, we can say, well, how far is each point from that line? And then, of course, we're left with one other important source of variation that we can calculate in this data set, and that is, what is the overall variation of each individual point from the line, or from the mean. So if the mean is a better estimate, then we're going to have, we can calculate the distance from each individual point all the way to the line here, right? So each individual point can go all the way to the line, and a lot of times that's going to look like this, the combination of the other two sets of dots that we drew. Go from the point to the line, excuse me. Okay, so in each of these cases, from our black dot, we can go all the way back to the line. Just clean up my drawing here just a little bit. And we have one more source of variation. And that's going to look an awful lot like something we've seen before. In this case, it's going to be the summation of our y sub I minus the y bar squared. Okay. In each of these cases, these are all really called sums of squares. Because in all cases, we're talking about squaring the deviations of individual points from some other estimate of where they ought to be. Either that's the overall average, or it's our line of best fit. In the case of the error term, we minimize that in the first place to get our regression equation, our line of best fit, or our least squares regression. But when we add up, take all these points in combination, we can use them to say something about the quality of that line, the strength of the fit with regard to variation in the overall data, and even the probability that this line would occur due to chance alone. So now we're going to shift away from this, and let's go to the table. Hang on to these individual points. If you haven't written down these individual portions of the equation, you might want to write them down in your notes now, and then we'll transition to the table. When we go to the table, you're going to see this exact same setup with regard to the squares, but we're going to take it further and calculate some more items from it.